Once again, thanks for being here right in the middle of your week, in the middle of the afternoon. I'm Alex Ecaldi. I'm the General Secretary of the ETPN, the European Technology Platform on Nanomedicine. And as you might know, we're in charge of the communication, dissemination, and exploitation part of the Metrino project. Today, we have quite an exciting program, and I will welcome very soon on stage our two great speakers today. But I'll start by just some, let's say, short presentation and housekeeping slides so that everything else runs smoothly. Welcome anyone and everyone to this new edition of the Metrino Academy. This is session number 2. It's a monthly webinar series designed to bring practical, usable guidance to the European nanomedicine system. Metrino is a Euramed project, and we are not here just to throw knowledge, data, materials, but to make it really to make a change in your daily routine in your nanomedicine lab or company. So today it's the second session. We'll welcome Christian and Yuri in a few seconds, but we will dedicate to how to choose the right measurement methods and to make it a practical approach. And we know how useful it can be because virtually full characterization of nanomedicine is virtually impossible. There are too many possibilities, too many criteria to measure. They can be critical or not. You have 3 methods. You have tons of manufacturing system that can help you measure that. So you need to find the right critical pathway. And indeed, our dear guest will help us on that. Agenda, we're a bit late, 5 minutes, so I'll move very fast to explain what is the Academy, what is Metrino. And we'll move on to the main part, which is the talk. But I should not say the main part, because the main part is the Q&A. We wanted to make it very, very interactive. So you'll see that you have different interactive sessions during this webinar. And please play that game and answer our interactive polls that help us a lot to shape the action in the future. Some housekeeping. So please put your cameras on, your microphone. You cannot unmute yourself by yourself, but during the Q&A, I will indeed give the mic back to you if needed. The chat is disabled so that we focus on the presentation, but please find the interactive Q&A tool. So you look at plus or Q&A or the 3 little dots and you have Q&A, and you can ask your question during the slides, during the presentation, and you can vote for your favorite question. We will start by the question that got the maximum number of votes. So don't be shy. There's no bad questions. And also, if we did not have the time to answer all of your questions, I'm sure that our dear speakers will be happy to answer by written form if it's really a crucial question after the webinar. What is the concept of the Metrino Academy? It's very simple. We take every time one key nanomedicine challenge, like today, choosing the right measurement methods, and we try to make it a very hands-on experience with something that is actionable, not just knowledge or data or results. And it's a monthly community rendezvous. So I know that some of you were already here for the first fantastic webinar with people from Nanobiotics talking about industrialization constraints. And the next one also, I will announce it right after. Metrino is a Euramed project, Euramed standing for European Association on National Metrology Institute. Everything that we do is about democratizing and refining metrology standards in nanomedicine. So it's a meeting between these two communities, people that know how to measure properly and precisely, and people that produce nanomedicine products. It's a big consortium with indeed the National Metrology Institute, but also universities, large research and technology organizations, pharma companies, an SME hospital, and the ETPN Association. Okay, so if you want to learn everything about Metrino in 1 minute, our dear coordinator, Robin, we made a video of him where he tells you Metrino in a nutshell in our website. And I strongly encourage you to visit the website because it's really active and you have a lot of content, but also a lot of fresh news. And it will be more and more dense packed with contents until the end of the project. So I hope that you won't waste your time by visiting our Metrino website. 3 pillars. Metrino in 3 words. We try to shape a roadmap for the development of certified, at least reference materials in collab with industry. We want to provide you with SOPs. So developing and harmonizing standard operating procedures for the characterization of nanomedicine. And also we try to somehow create a new community of people of the metrology and nanomedicine community that get used to work together and to create some kind of common culture on how to do better nanomedicine. Okay, who we are. I won't go too much into details, but we have some of the most important people, work package leader around the table, like Christian today, Robin, Enrica from LNE in France, Ute from BAM, indeed Leonardo from INRIM. So it's really a pan-European project. And yeah, the core part of it are the National Metrology Institutes, indeed. This is the DNA of Ramet calls. Who you are today, more than 60 registered participants. As usual, three quarters from academia and almost the rest, from industry and other institutions, with a large variety of people coming from not all Europe, but more than 10 countries today. So please feel welcome. It's the first time you come. Be welcome. And you can access the rest that you missed last time without any problem, because we've published a full article with not only the replay, but also an easy way to have the insight of this session on how to scale up from lab to clinical studies, your nanomedicine manufacturing, your characterization, etc. It was a fascinating insight from nanobiotics. I strongly recommend that you go and have a look at the replay. Okay, but let's move on with the people that we are super happy to have around the table for this session too. First, we have Dr. Christian Gollwitzer. Good afternoon, Christian.
Hi.
Hello. Yeah, so Christian has a PhD in physics from the University of Beirut and Charles University in Prague. And he received his doctorate from University of Beirut in 2010 on the topic of magnetic gels and liquids. And after a postdoc at the Federal Institute of Material Research and Testing, BAM, in the field of radiography, and at the German National Metrology Institute, PTB, on small angle X-ray scattering, he returned to BAM to work on the field of computed tomography. And more recently, for the last 6 years, he's been working back at PTB, and he's leading the working group on X-ray radiometry. And he's really a pillar of Metrino, always having fantastic ideas. So, Christian, thank you for being here, and I can't wait to listen to your content.
Thank you for the introduction. So
You're
Yuri is sharing the slides.
Maybe I will just present our second speaker, Christian. Come on.
Sorry.
No problem. Good afternoon, Yuri. Yuri Antonio Diaz Fernandez. Yuri is a senior lecturer of the Department of Chemistry of the University of Pavia in Italy, with a very long-standing international research career in nanotech, surface science, and colloidal chemistry. He has held research and academic position across leading institutions, including University of Liverpool, Chalmers University of Technology, and the Nano Bioimaging LGC Group in the UK and Sweden. So Yuri's research focused on the design, synthesis, and character of nanostructure materials and supramolecular systems for applications ranging from antibacterial surfaces to catalysis and sensing. Dr. Diaz Fernandez has secured competitive research funding, published extensively in high-impact journals, and contributed to an interdisciplinary project at the interface between chemistry and materials. He's indeed a member of the Royal Society of Chemistry and holds affiliation with international research networks. And this is fantastic, but also he's the only one that dared to say yes when we say we want someone to help us build a decision tree for how to choose the right characterization method. So thank you for the crazy idea, Yuri. Please feel extremely welcome today, and I'm happy that I have two fantastic experts around the table.
Thank you, Alex. Very kind.
And if I may, for those who doesn't know, Clémence that spoke at the beginning, Clémence is the new hired employee at the ETPN, and she's in charge of project management together with me. And yeah, she will give you a lot of support, better than I do in the coming months. Feel welcome, Clémence.
Thank
Okay.
you. Thank you.
So just to let you know, so Yuri, Antonio, the floor is yours for 40 minutes.
Okay, so thank you very much for the warm welcome, for the opportunity to start here. So our webinar had got the title, Choosing the Right Measurement Method, a Practical Approach. Can you go on? So you have probably seen this slide before. It's the Metrino advertisement slide, which we use. It's very nicely designed by our experts from ETPN, and we use it to advertise the Metrino. And when you have a close look at this slide, you see that there's a lot of metrology in there. So the name of the project is Metrology for Innovative Therapeutics. It's from a metrology partnership. And there are 9 national metrology institutes involved. So you might ask yourself, if you're not from a metrology institute, what is metrology and why should I care? Can you go on? So what is metrology? Strictly from the dictionary, metrology is the science of measurement and its application. And it also has this helpful subtitle. Metrology includes all theoretical and practical aspects of measurement, whatever the measurement uncertainty and field of application. I'm not sure if this makes it more clear to you. So I try to break it down into like 3 simple statements. So metrology can answer these questions to you. When you have a measurement, how accurate is the measurement result? So what is the deviation between your result and the real truth? Then the second question, when you have 2 measurements, how can I compare those? Are they the same or are they different? And the third one, most important, what method should I choose for my sample?
Christian, first, I propose that we launch the first interactive questionnaire right now. Okay, so you can all answer very easily. We'll take just 30 seconds to do that. We have 2 questions for you. The first one, which of these methods do you currently use for characterization of your nanomedicine? So dynamic light scattering, nanoparticle tracking analysis, electron microscopy, field-free fractionation, atomic force microscope, other, or not currently doing any characterization because you don't care. That's question number 1. Question number 2, what is the most important measurement right now for you in your research? Size, what a big surprise. Particle concentration, surface charge or zeta potential, payload or encapsulation related metrics, stability and aggregation. And now I will just show the results. Enormous surprise, DLS and electron microscopy are the first one. And also, would you guess that size is still the most important measurement for people? Well, indeed, we saw with nanobiotics that just caring about size is not enough. And sometimes it's not the critical parameters. But yeah, so we have quite classical answers. But now I leave you the floor back to you, Christian, because we'll going in more nuanced situation, I guess, in the coming minutes.
Exactly. Thank you very much for these results. Yuri, the next slide, please. So in order to show to you why we actually need this metrology science, I brought to you an old example. It's from 2012. On the left-hand side, you see an image of particles. They come from the Institute for Reference Materials and Measurements, and they are silica particles with a nominal diameter of 40 nanometers. This is a reference material, and you can still buy it under the link that's shown below. And back in 2012, we conducted a study with several instruments and several metrology institutes, so people who really know how to operate their instrument. And I've plotted all the results sorted by size. And you can see that the lowest result is below 25 and the highest result is above 40. And the nominal size is about, is 40 nanometers. So the question is, which of these results is actually the correct one?
And this is the result. The majority of you told 26 nanometers, AFM, TSEM, and SAX.
So only a small number of people. So please, Yuri, can you go on to the next slide? Okay, so not spoiling. So there are arguments actually for each of these answers. The DLS could be the correct one because it is most closest to the 40 nanometers that we got from the IRMM. So we would expect something like 40 nanometers. Then for the second answer, the AFM, SAX, TSEM, they are very close to each other. So we have multiple measurement methods which each complement each other or which each confirm each other, which is also a strong hint that it could be the right result. But if you don't believe any of them, you could say, well, it should be somewhere in between. Let's go to the golden middle. And then it would probably be the SEM result with 35 nanometers. And now you can go to the next slide, Yuri. This is actually a trick question. And none of these answers is correct by itself. Because if you only have these measurement results that I've showed you on the graph, you cannot actually decide which one is the correct one. in order to decide if they are comparable or if they are correct or whatever, you need the uncertainties. And now you see on the right-hand slide also the results plotted together with the uncertainties. For example, you can see that the SEM value has a large uncertainty. The value where they believe the result is in extends from 30 to 40, whereas the DLS result is within 1 nanometer at the 41 nanometer result. Next slide, please. So the real answer, the metrology answer is when you have the uncertainties, you can do much more by comparing the results. So comparing two results means that you evaluate the uncertainties if they overlap. For example, if you look at the result from the SEM and you compare it with a TSEM result, like next to it, you will see that the error bars, the uncertainty ranges, do not overlap. So these results would not be compatible. But if you compare the SEM with the next one to the left, the in-rim AFM, you see that the error bars overlap. So these results by itself, if you have no other information, they would be compatible. Then if we have these uncertainties, we can also build something like a middle, like an average. And if this works by, if you have compatible values for each of these measurements, you average them, but they are weighted by the uncertainty, so that if you have a more accurate result, it influences the result more. And if you have multiple results and the values are not compatible, then we can apply some more sophisticated math to come up with a reference value and to detect outliers. And that was done in the paper that is cited below the graph. Here, the authors applied this sophisticated value and found out that we have to kick out these SEM and DLS results, and they also kicked out the AFM in-rim result. And from the rest of them, they built the reference value. This is the yellow shaded area. So this is the reference with the uncertainty, which is about 26 nanometers. So most of you guessed 26 nanometers is the correct result. That's in some sense it's true, and the idea that the other results confirm each other is the reason for that is also a good idea, but without uncertainties we cannot really know it. Can you please go on? The one question remains: if you look at the DLS result, it's totally out of range of the other results, especially if you compare it with the uncertainty. If they would have said the uncertainty is 20 nanometers, it would be fine. But it does not even come close to the reference value. But it's the one that the IRMM provided because they also use DLS to provide their reference value. So why is that? The reason is that these methods measure different things. So how do you define the diameter of a particle? So if you use AFM, you use a needle and you touch the particle. You move the needle until you touch the particle. When you use an electron microscopy, you shoot electrons at the particle, and these electrons are scattered by the electrons in the particle. So it's basically the diameter of the electron cloud contained in the particle. When you use SAX, you do basically the same thing, you just hit it with photons. That's the reason why usually the diameter by SAX and TM is relatively comparable. And also AFM somehow interacts with the surface of the particle is also more or less the same. But if you use DLS, what you actually measure is the Brownian diffusion motion of your particles. And from that you derive somehow the size by the friction of the particle in the water. And this is called the hydrodynamic radius. This hydrodynamic radius is basically just what DLS measures. So the answer why it's so different is each method has a different measurand, and the result you get from DLS, it's not wrong. It's just a different result, which is not comparable to the others. Can you go on? So how do we get these uncertainties? In metrology, we call this traceability to the SI unit system. So this means we have a measurement and we want to know this uncertainty. And the first thing we have to do is define the measurand. So if it's the hydrodynamic radius or if it's the other radius, then you have to figure out what influences these measurements and do some calculations. And this traceability basically is a comparison of your measurement method with some standard, then going back usually to some NMI, Metrology Institute. And this relies on the definitions of the SI unit system via an unbroken chain of comparisons. And there are two ways to do this. There's a hard way and a less hard way. And this will be my final slide.
Maybe we should try, we have an expo right now to try the ability to talk about uncertainty, Christian. So I will launch it right now.
Yes.
Once again, 30 seconds. How well do you know the uncertainty of your method? So I quantify it and I report it systematically. That's the expert mode. I know how to quantify it, but it's not required for my work, so I don't spend time and money on that. I know how to quantify it, but constraints like time, resources, training, skills prevent me from doing it, sometimes just budget. I would like to quantify it, but I don't know exactly how to do that properly, or I'm not sure what measurement uncertainty means in this context, which is perfectly fine. So 30 seconds to answer. Okay, so I hope you see it. We have a majority of expert people around the table. That's perfect. But we also have a significant amount of people that really do need your expertise, Christian, because they want to quantify, but they're not sure how to do that. So let's go to the second part maybe of this presentation by Yuri, if I'm not mistaken, right?
So this one is still by me, this slide. So you have one way to do this traceability. This is what all the NMIs do, and probably all the people who reported with option 1, I know how to do and report it. They use this way. So you build a mathematical model of your measuring device, and then you simulate all the influences that you have from the different environments and the parameters. And then you compute this uncertainty. This is really the hard way because for that you need to build this mathematical model. But there is an easier way that is used by most analytical labs. If you can find a reference material that was somehow measured by an NMI, that is very similar to your sample. That is the key here. You need some reference material that is as close to your sample as possible. Then you can run a certain series of measurements by measuring this reference sample, see what your device reports, then do repeated measurements on the sample on several aliquots. And by that, you can estimate the so-called top-down uncertainty. I've also put a reference here for how to do this. And then it's relatively easy, but the requirement actually is to get hold on this reference material. Okay, now it's Yuri.
Thank you, Christian. So I will move on with the presentation. Okay. So in this second part of our talk, we're going to discuss to showcase some examples from Metrino, examples of the research that we have been doing in Metrino, in which we were focusing into applying these metrology approaches to assess critical quality attributes of nanomedicine, especially in terms of size, particle concentration, and chemical homogeneity. Of course, for what Christian was saying, you could, if you are not still aware of this, you could hint that the need of several techniques to analyze complex systems and nanomedicines depends also on the nature of the sample, not only on the measurand that each of the techniques is measuring, but different type of materials will require different sample preparation procedures and different techniques to assess specific measurements. And in addition to that, we will also discuss some ideas of how to deal with the matrix interferences in these determinations. The first example that I'm sharing with you is an example of an MRI, so a magnetic resonance imaging nanomaterial-based contrast agent produced by Nanopet, one of the partners within Metrino, that is called Ferraspin R. This is a magnetic resonance imaging contrast agent that is already in an advanced stage of clinical trials. And one of the critical parameters that you need to assess for these nanoparticles is particle size. And here I'm showing you two different techniques, electron microscopy techniques, to assess the size of the particles. In the top row, you can find scanning electron microscopy, which is a sort of solid state technique in which you need to dry the sample in order to measure. And in the bottom row, we are showing you the data on cryogenic transmission electron microscopy, in which you manage somehow to freeze the sample and to keep it hydrated in a frozen condition while you're doing the measurement. And of course, in these two different conditions of sample preparation may lead you to different biases on the determination of size. Because if you freeze the sample, you keep whatever was in solution at that moment, while when you're drying the sample, you may have zone effects due to aggregation or agglomeration of the particles. And what we demonstrated is that you can validate the SEM, so scanning electron microscopy sample preparation methods, by using a complementary technique that allows you to measure the same measurand, but with a completely different sample preparation procedure. And you could see that the size distributions, that for those who are not familiar with, this is the percentage of particles in number as a function of size. You can see that both size distribution measured with the two techniques are quite correspondent. So you find a correspondence between the sizes measured by cryo-TEM and SEN, validating the sample preparation in this case. There is also a different technique that unfortunately, I will talk very fast on it because I'm not particularly an expert. If you have any question, Christian is one of the core techniques that he's leading within Metrino, that is a small angle X-ray scattering. This is also a technique that provides you information on the size of the particle. But in this case, it focuses on the size of the core of the particle, not the geometrical external size that you may see in SEN or cryo-TEM. And what we found is that since cryo-TEM allows you also to determine the size of the particle core with some imaging processing methods in order to segment the cluster of particles, we found a good correspondence also for the core measured by cryo-TEM and the SACs. And when you put all these data together, so the size distributions and the statistical parameters, there are a few things that just immediately comes that call your attention in this table. That I know that there are a few numbers, but I will try to guide you very quickly on how to interpret those. No? So what you could see is that in terms of the mean size of the particles, the value from SACs, cryo-TEM, and SEM are quite correspondent, as Christian was saying before, because they are assessing the same parameter. While there are other statistical parameters or other descriptors of these size distributions that you may use to predict in a certain way the size parameter. And as Christian was saying, it's not that one of these parameters is the correct size value. They are just simply differently in the way. Sorry? Oh, okay. There is someone that is okay. So they are just simply different descriptors of the same particle size, but depending on the one that you choose to describe your system, you may find more information, or it could be more useful for certain approaches. No? And particularly because you can, as Christian was saying, compare these particle core measurements or particle size measurements with other techniques that measure slightly different measurements, like in the case of DLS, of asymmetric flow-free flow fractionation. And the first thing is that you can classify these measurements in terms of single particle measurements. So particles, it allows you to count particle by particle the size, like microscopy techniques, and ensemble measurements, in which you measure the whole sample and then obtain an average value from that. No? And secondly, you need to divide these techniques in terms of the measurements that they can measure, because in one case you're measuring the particle, the actual geometrical size of the particle, while in the case of dynamic light scattering and asymmetric flow-free flow fractionation, the last column in the table, you measure the aerodynamic size. And you see that across Metrino, because this is data that we have been just accepted as one of the first papers from the consortium, you can see that they clustered, not depending on either if it is single particle or ensemble measurements, but they cluster depending on the measurand, and that's critical, no? So in order to compare this data, you need to know which measurand you are taking. Coming back a bit to just remind us what we said before, cryo transmission electron microscopy is based on a Nobel Prize worth winning work of Dubuchet, that he created sample preparation procedures. So he launched sample preparation procedures in order to preserve the particles, whatever they was, either proteins or nanomedicine particles, preserve their morphology and structural properties, and allow the high resolution or high magnification analysis using transmission electron microscopy without dehydrating the samples and minimizing also radiation damage. And this is what allows you to do electron microscopy on very, fragile systems, like for instance, liposomes. So what I'm showing you here is a set of a portfolio of liposomes. Some of those, the ones in the bottom row, are produced by one of the Metrino partners, Curadigm, and the top bottom ones are liposomes produced at the University of Pavia, and then we compare across these different compositions, different formulation of the liposome, also different size ranges, the properties using cryo-electron microscopy. All these liposomes are prepared using the classical thin film extrusion method. No? And what you could see is that the morphology and either the internal morphology of the liposome is preserved, and you can count the single lamella layers that are formed there. I hope that the resolution of the image is good enough in the screen that you can see that these are single lamellar structure sometimes, and sometimes they are multiple lamellar, but you preserve that very fragile structure under the electron beam microscope. And that allows you to, as we did before, for a hard particle, because ferrous PNR is based on a hard material, while liposome has very soft and fragile, this allows us to do the size distribution in the same way, no? And when you compare the size distribution of the different liposomes, the first thing that you notice that is also in line with what Christian was saying before, is that the nominal size, the one that you will expect from the specs of the membrane that you use, is different from the one that you measure for any of the techniques that you may use. And this is due to the fact that this is just the nominal size of the pores of the membrane that you use for the extrusion process. But when you measure, you find actually a different one, and actually, depending on the measurement parameter, you may find some differences. But I will take you to that in a minute. One of the critical parameters in the case of liposome is quite important, but for all the particles, or in nanomedicine especially, is the polydispersity index, that you can determine with different techniques. In this case, this is reported from multi-angle dynamic light scattering, and the lower this value, the better the liposome is. And you can see that in wide range, so anything below 0.2 sometimes is considered a very well monodispersed population, because of course, if you want to go through a regulatory pathway, you need to have a very well-defined system to work with. No? And then, as I was mentioning before, when you compare the sizes that you obtain for cryo-electron microscopy and from multi-angle dynamic light scattering, you see that there is a bias. And Christian sort of spoiled that the answer. So we could have made a pool also here just to see if you were really listening for what Christian was saying, because what we have in here is two different measurements. So by cryo-EM, we are measuring actually the geometrical size of the particle, while we measure dynamic light scattering, what we are measuring hydrodynamic size. Interestingly, the bias in this determination is too high to be explained just by simply hydration layer around the liposomes, especially because in the hydrated state, we will not expect the liposome to collapse, so they will have the exactly same size that they had in solution before. And there is another thing to take into account, and is the fact that generally cryo-EM imaging is reported as number-based average, while dynamic light scattering is intensity-based measurement. And we know that intensity-based shift the values towards high value, because higher particles are high intensity with respect to smaller ones. So when you go to an intensity-based average, you will have higher values with respect to cryo TN. In this case, that is number based. And this takes us to our first checkpoint, and I will leave the floor to Christian with our first decision table for the techniques.
Yes, so we thought about how to compress all of the knowledge that we gained in Metrino and then also in previous projects into something that is easy to digest for the practitioner. And we came up with this so-called decision tables. So this shows a few of our different types of materials that we analyzed within Metrino and a few of the measurement methods that were considered. So for size, we had electron microscopy, DLS, SAX, NTA, and cryo-EM. And for example, you see like this angry face for the electron microscopy for the soft particles, liposomes, LNPs, because they work in vacuum, so they cannot you cannot measure particles in suspension there. They would be gone bad. Or a similar thing is when you use SAX and you have polydispersed samples, it becomes not so easy to use or maybe unusable. But if you use SAX, you can use it easily for very small particles where other methods struggle a lot. And when I see at this table, I can easily understand why most of you answered they use DLS, because DLS does not give the best results if you consider that it's a hydrodynamic radius, but it works across the board relatively well. And we have a similar table also made for concentration. So for concentration, it's much angrier because there are not so many methods which can reliably measure concentration. For example, the electron microscopy doesn't have any way to measure concentration. Would be very good, and it's currently being developed in one of the follow-up projects, but at the moment it's not available. If you look, for example, at the NTA, it gives relatively good results for concentration, but it has a very small lower limit of detection. So if you have small particles, then your method would struggle. And with DLS, the problem is that you need refractive index of your particles. And most of the time, it's just a guess because it's very hard to measure that. So, I mean, we will share this. I will not explain the whole table, but give the floor back to Yuri for the chemical concentration.
Thank you, Christian. But just before going to talk about chemical composition, I just promised, we promised that we'll discuss the effect of myological matrices, also with an example from Metrino. So these are curadyne liposomes, and what you are seeing here is the size parameter, set average, in this case is indicating a weight of calculating the average size of the particle by DLS. And interestingly, what we have done is measuring the size of the same liposome batch, but in different media, in different matrices, liquid media containing different chemical compositions. In the first case, so the sort of completely gray with no texture column, bar, let's say, what you can see is a phosphate buffer saline, so PBS. Then the intermediate one is so the simulated blob matrix with no protein. And then the third one, what you get is the PBS matrix, but supplemented by fetal bovine serum. So just to make to cut a long story short, what we have in the two first cases is just ionic strength effects. And in the third one, we add the complexity of a protein environment, a protein-rich environment. And for those who are familiar, with nanomedicine or have worked with nanoparticles in protein-rich media, this data is showing something that is contradictory to what you will expect, because what you see is that there is a reduction in the size in the presence of the protein. So there is extensive literature saying that when you add protein to something, the protein has the ability to attach to surfaces of any sort of particle, and then what you see generally is an increase of the size. No? But what we observe here is a decrease in the size. due to the presence of these proteins, which was somehow at the beginning was a little bit puzzling because we were not able to understand what was happening. And interestingly, the polydispersity index, that's the other parameter that I introduced a few slides before, when you add the proteins, it just simply goes really, really high, indicating that in addition to the original population of particles that you have added, you have something else that is somehow interfering with the measurement. In order to elucidate what was happening, what was going on in this system, we use a separation technique, asymmetric flow, free flow fractionation, that have been a common effort across several partners within Metrino. And this is a technique that allows you to connect a separation, so a size-based separation method with detectors that allows you to characterize downstream, so hyphenated, in a hyphenated way, you can characterize the size of the particles and many other properties. No? But the important thing is that since it is separating by size, it can separate small proteins, so the matrix itself, from the bigger particles. And that's exactly what we obtain when we use AF4 to separate, to analyze the particles. What I'm showing you here is two examples, two data sets of an AF4, so we call it colloquially like that, AF4, asymmetric flow, field flow fractionation, because it's too long, no? Otherwise we will need 2 hours for the seminar if every time I'm saying the full name. So we'll call it AF4 for friendly, let's say. And what we get is that when you do the measurement in PBS, you see this profile. That is a sort of, for those who are familiar with those techniques, it's sort of chromatographic size exclusion technique. It's not working that way, and we don't have time to explain the details, but it's just separating the thing by size. And what you see is a distribution that follows somehow the size. When you use in addition to the PBS, you got the PBS supplemented with the proteins. What you see is a very high peak at the beginning. That is, all the proteins have been eluted before and separated from the particles. And then you can actually, that's why it's called a fractionation technique, because you fraction the small things from the bigger one. And when you do that, so when you remove the matrix, you return to a value that is consistent independently of the matrix. Because what I'm showing you here is the results. The first that we saw before in the previous slide, when you measure together proteins and the liposomes, and you see that there was a bias. That's what we mentioned before. No? In the presence of the protein, the size of the particles that we effectively measure were slower. But when you remove the matrix, you return, I mean, statistically speaking, you return to the same size that you had without the protein. So that means that the proteins are not actually affecting the size of the particles. The particles are preserved and are stable under dark conditions, but the presence of the protein is interfering with the measurement of DLS. And this is because protein can aggregate, they can also increase the scattering events, but since they are way smaller than the liposomes, they will bias the measurement in batch towards smaller values. And this is, of course, opening opportunities to use AF4 to analyze these systems in complex matrices. Like, for instance, so feta-bovine serum is a model for more complex biological fluids. The final part of our talk will be focused on chemical homogeneity. We were spoiling just a while ago, no? And in this case, we return to the ferraspin-R, so to this nanoped magnetic resonance imaging contrast agent based on inorganic, on solid nanoparticles, and we investigated the chemical homogeneity. And one of the things that when you try to investigate a micro or nano heterogeneous system with some analytical techniques, you realize very quickly that the size, so the sample size, may influence the variability that you are trying to measure. And this is what I'm showing you in this table. So this is data that have been accepted for publication and nanoscale advances. And I hope that in the coming weeks it will be out. And what you see is that by decreasing the sample size, by going to analytical techniques that sample smaller portions of the sample, you see an increase of the variability. And then, of course, coming back to the questions that we were telling before, then chemical homogeneity, how do you find chemical homogeneity in a system like this? No? So how can, which of the 2 or the 3 or the 4 or the 5 different chemical homogeneity descriptors that you are obtaining with different analytical techniques can you take as the real homogeneity value? And the answer again is only probably the only sensible answer to this question is only one, and it's just returning back to the speaker the question. So it's not that there is an answer to this question, but that the question has been formulated in the wrong way. There is no of these homogeneity values, let's say, that is the correct one. All of them are correct at a different length scale. And then if you are trying to assess homogeneity of an injectable alcohol that is a few milligrams, then you can rely on TGA or ICP-MS that are bulk techniques that analyze a relatively large amount of sample to assess the homogeneity. But if you are trying to investigate with a microscopy technique the biodistribution inside a tissue sample or a cell culture of your nanomedicine materials or carriers, then of course you cannot rely anymore on that chemical homogeneity because you are not analyzing milligrams anymore. So you need to then rely on a different length scale and a technique that corresponds to that length scale. In this case, well, for instance, like semi-DX or XPS. There are techniques that, of course, we don't have the time to go into the detail of those, but I'm pretty sure if we will share the slides, that you can get more information about how these techniques work and how it's possible to cover this huge length scale coming from milligrams down to micrograms of material that you analyze with the spectroscopic techniques. And this taken for one of the very, it's not the last one, but almost the last station of our journey, in which we want to introduce, following the same concept that we did before for particle size and for particle concentration, to share a decision table, or more than a decision table, like sort of suggestive, let's put it this way, table to choose which techniques is good for what. And then what you can see is that there are some small, like in the phone contract lines, that you have very, very, very small lines that you say, okay, this is good, but remember that, like for instance, micro-Raman is a fantastic technique, it's very versatile, but it will give you only relative amounts. So we'll not be able to quantify exactly what is the content of what component. You can assess chemical homogeneity and chemical composition, taking into account the relative intensity of the peaks in the case of Raman. And it's something similar to FTIR, with the difficulty that in the case of Raman, you can do micro analysis. In the case of FTIR, unless you have a micro FTIR, that this instrument exists, although it's not so common, generally you will use an ATR, FTIR, and you will need a little bit more of material, and you cannot go micrometer scale, let's say. No? In the case of electron microscopy techniques and other techniques that they work in the vacuum, of course, any sample that will not survive vacuum will be quite hard. That is why, for instance, XPS, that is pure vacuum, and cryo-XPS, that works also in vacuum, but you can freeze your sample before analysis, then you can use it also on soft particles. So if you got inorganic metal oxide nanoparticles, in this example that we were telling before, ferraspin-R, you can use either XPS or cryo-XPS for the analysis, but if you have soft particles, you need to understand what is the chemistry that, and the physics that is behind sample preparation and the conditions of it. One example that is also widely used, although it's still being developed as we speak, so and we expect that in the coming years it will be even better, is using ICP-MS to analyze single particles, also to the single particle level. So the instrumentation have been pushed to the level of analyzing even single particles, and in this context, you can use also single particle ICP-MS to measure concentration, particle concentration, because you count them, the events in the ICP-MS. You can very, very easily analyze, not easily, but I would say you can rely on ICP-MS to analyze metal oxide particles. If you got liposomes that will contain some sort of metal inside, you will struggle a little bit because metal concentration may be a problem, and then you will have problems with the size. And if you go to pure lipids, it will be quite hard to be analyzed. On the other hand, another mass spec technique, but that does not rely on plasma, but rely just simply on a classical chromatographic separation technique like HPLC-MS, will be blind to the inorganic component, but will allow you to determine the chemical composition of a complex mixture of lipids in the case of liposomes or lipid nanoparticles, or any, for way of saying, organic components in your system. The almost final stage before the acknowledgement, a couple of take-home messages that we want to share is this. This is not from it's not from Metrino, it's not from our pool, so I'm just referencing the original source for these infographics, but I found that it's quite explicative of what we are discussing here, and it's the fact that in addition to all the things, so the information that we have shared so far, you need to also think on the sensitivity of the techniques for the specific application that you want to achieve. And generally, as you reduce the spatial resolution, as you reduce, for instance, talking in microscopy methods, as you reduce the spot size that you can analyze, you also reduce the chemical sensitivity. You lose chemical information as you go down. And then that means that techniques that will allow you to analyze elements in traces, you will need large amount of sample. Techniques that you can go really high in resolution to the nanometric or micrometric scale, you will need to go high in concentration, or at least you will be able to analyze only analytes that will be high enough in concentrations. I mean, of course, we don't have time to go through all this, and it's not exhaustive, this list, but at least give you an idea of the breadth of techniques, of the methodological challenges of putting all this together in a single framework. So from this part of the presentation, just a couple of take-home messages that we want to share with you is the fact that we must stress that reliable sample preparation methods are critical. So you need good sample preparation method, and you need to compare methods with different sample preparation methods in order to validate and to correct eventual biases that you may face. Complex biological matrices could be a nightmare, and you need to be prepared to deal with it. One of the solutions, at least within Metrino, that we are proposing is to use the appropriate separation methods to separate the matrices from the actual particles if they survive this process, of course. And finally, to remind you that chemical homogeneity is also a matter of length scale. So to assess chemical homogeneity and to compare data of chemical homogeneity, more importantly, from different techniques, you need to be aware that although you're measuring maybe the same exact parameter, the same measurand, it is a measurand measured at different length scales. And so that's why you cannot directly compare them necessarily. And you need to be aware of this. No? And with this, I think that we can close the presentation part, just acknowledging all the people that have contributed to the data that we have presented today. This list is not exhaustive, so please, if we forgot anyone, don't blame us for that, and don't take it personally, because we just covered the people that produce data for the data we were presenting in these slides. But there are a lot of other people with discussions and very fruitful conversations across Metrino that have contributed indirectly or directly to the success of this project. No? So thank you very much, and I pass the floor to Alexander. Thank you.
Thank you, Yuri. Absolutely excellent content. I mean, yeah, I've been in that game now for 10 years, and that was one of the most comprehensive way to understand how to better measure your nanomedicine product. Thank you, Christian. Thank you, Yuri. Thanks a lot. Now we are moving to the last part, which should be the most interactive part of this session, which is the Q&A. So as you know, the chat is closed, but you should use only the Q&A tool. If you can't find it, check at the bottom of the Zoom tool. You have a plus with 3 little dots. You click on it, and you easily find the Q&A tool. When you do that, you can ask your question, and we will start by the most voted question. Right now, there's no question, no problem. Just to break the ice, I know you were, let's say, starving for a new poll. So here's a new poll, just to see exactly what is your biggest challenge right now in the crowd in terms of characterization. You can do both. You can answer the poll, and you can indeed ask your first questions. So yeah. What is your biggest challenge in nanoparticles characterization? Sample preparation, choosing the right technique or combination, data interpretation or avoiding artifacts, comparing results across labs or instruments. I'm a bit worried that you don't consider it a challenge. Traceability, uncertainty, and documentation, or just others. So please take a few seconds, and also don't forget to ask your tricky questions. Otherwise, we have some. Well, I'd like just to take a few minutes to thank you also, Christian and Yuri, for taking the time of doing these kind of heat map, emoji maps, because I guess that it's really a very nice way not to do mistakes and try to choose at least from scratch the right methods. Okay, I will close now the poll and show you the results. There's a lot of work to do, guys, because I mean, yeah, there's a lot of work to do. It's not obvious at all. And yeah, it's quite even between sample preparation, choosing the right technique, interpreting data, comparing results, and traceability. So as I always say, as a joke, nanomedicine is simply impossible. But I mean, it does work. But yeah, you do need support. So what I suggest is that maybe I start by, so my first question is that, are you too shy to ask questions, or simply you cannot find? Oh yeah, okay. I have a first questions coming, so that's nice. I will ask the first question. So it's from Matteo Sodano. Very nice, the slide concerning the overview of different analysis technique to apply at the detection of the different nano category. Okay, right. I mean, that's more a comment than a question. So if I may start with my own question maybe, and I'm sure that some other will come. Okay, very non-expert question, Yuri and Christian. Okay, like from the crowd, from the field, for a non-expert like I am. If someone tells you, okay, I need the particle size, which is a simple question and simple reflex, what is the clarification question that you would ask before recommending any method? So yeah, what would be the first top advice to a junior or a student that needs to know the size?
So maybe this is a question for me to answer. So first I would ask what you mean by size. He may be confused by it, but as I've shown, there are at least two different reasonable explanations. Most particles have some kind of core and some kind of shell. And do you want to know the overall size, or do you have some hard core that you want to know? And the second question, of course, would be what's the material? Because as you've seen in the table, it's mostly structured by material. And the third question would be, what is the size that you expect? So if it's like 5 nanometers, you would use a totally different technique than for 400 nanometers.
Excellent. People are too shy, so I ask a second question. Oh no, okay. Robin, our coordinator. Thank you. For particle size, I should use, for instance, ensemble methods like DLS, SACS, and particle by particle methods like them. What methods should I have at hand to characterize the particle surface? Yuri.
Sure, sure. But before answering this question, just to add something to the, I mean, very complete question that Christian said, so like just complementing, is because it's something critical that I probably forgot to mention during, so I was meant to, but I was rushing with the time and trying to get to the point. But actually what Christian was saying is that there are some properties. So because sometimes people, when you ask, do you want the core or do you want the hydrodynamic radius, they say, what are you talking about? No? So I think that sometimes it's always useful to translate that into actual practicalities. No? So hydrodynamic radius, for instance, it will determine biodistribution, while sometimes particle core will determine some fundamental properties of the particles. In the case of Platonic particles, it may determine the optical properties, for instance, no? Or it may determine also the magnetic properties in magnetic nanoparticles. No? So it's useful to correlate to what is the actual need, because sometimes people ask for size, but they really don't know what they're asking for. And then in terms of surface characterization, I will then use the same modus operandi that Christian was very cleverly using before. So we'll start with a set of questions first, I mean, before answering the question, no? Because surface characterization could mean many things, no? Because it could mean surface chemistry, it could mean surface charge, and if, for instance, if you want to measure surface charge, most likely zeta potential associated with DLS, or dynamic light scattering, would be one of the useful choices. If you want to analyze surface chemistry, probably XPS, So X-ray photoelectron spectroscopy will be one of the techniques that I would choose if the sample is compatible with these techniques, especially with XPS. It's challenging because it's a vacuum technique generally, Although we got the fantastic partners at MPL that they're able to do cryo XPS, So that is the next level in which you can preserve the sample as it is, more or less, let's say, But that would be my answer, the two first that come to my mind. It's not exhaustive answer anyway.
I mean, it's possible. Just to continue on that, I'd like to simulate a situation that I often see, which are having a DLS in-house in a lab, right? So what would be your first advice to make, very pragmatic, to make these measurements more reliable, okay? Would it be you recommend to systematically add a second method to do better or smarter sample prep? Is it about reporting or control? What would be your top advice for people using DLS better?
Wow. Should I take that, Christian, if you're happy with that, no? Yeah, so I think that's a very good question, Alex, because actually you need to know, I mean, so the DLS is a sort of sometimes unfortunate technique because you need to know a lot of your sample in order to use reliably that technique. You need to know, as Christian was mentioning, refractive index. You need to know the viscosity of the media that you are using. So you need a lot of information for complementary techniques already in order to arrive to DLS and to do it pragmatically. I mean, luckily, if you search in the literature, there are a lot of people that have been using these techniques, so you can find maybe data that you can try to apply or to add to your system in terms of viscosity of a specific media or the optical properties of the material that you are using. But the first thing that I will ask anyone to check is this, so that you got the set of parameters and settings in the DLS software in order to interpret that data. And then the second is to make sure that that either you are sure that your sample is monodispersed, that you got a single population, or that you couple this technique to a sort of separation, that it could be SAS exclusion or AF4 technique as a sample prep method, so that you just simply separate the different populations and then you analyze them in a batch DLS. As we have demonstrated also with some recent work related to Metrino, that's the winning situation, because then you remove any sort of bias related to multiple populations that are very close to each other.
That is a clear output of the project. You're absolutely right. Well, I hope everyone using DLS is as conscious as what you've just described. I'm not that sure, but I hope so. Next question from Matteo. Since the chemical homogeneity is different at different scales, which is the right one? And does it depend on the type of the sample or the intended use for it? Great question, by the way.
Okay, very interesting question, Christian. I think I should take that one as well, if you're okay with that, Christian, no? Yeah, excellent. So this is a very good question, because I'm pretty sure that will depend on the nature of the sample, not only on the chemical nature of the sample, but also on how the sample is displayed. Because of course, what you have sometimes is that you got micro heterogeneous samples, you got micro precipitation inside your sample, and of course, if you assess the chemical homogeneity with the microscopy technique, you will get some areas in which there will be richer of one component and others that will be maybe less, no? And the smaller you go, the higher this variability will be present, no? And that means that there is no clear answer to this question, or at least not an answer that we can say in 2 minutes. So we'll need to do another webinar just to discuss that question, probably, because it's very complex to assess this, and it's a work in progress. So within Metrino, we are doing a great deal of effort to try to understand this, how microspectroscopy can correlate to bulk techniques, and how you can put them all together in the same framework, no? Because they are assessing, actually, although you're measuring, even if you manage to measure the same measurand, and it could be, for example, the ratio between iron and zinc, for instance, no? So just to think, you got two elements and you're measuring the ratio between these two elements. If you measure the ratio with XPS, with semi-DX, with ICP-MS, you will find different homogeneity data because we are actually assessing different sample volumes, and it's almost like it's a different measure. Because in one case, you are measuring nano homogeneity, in the other one, you are measuring micro or mesoscale homogeneity, and in the other, you are measuring bulk homogeneity. And so,
We have more questions coming. People are less and less shy, which is a good sign. We have a few minutes, so please, guys, if you can make even shorter answer, that would be excellent, please. The next one. Thank you very much for the presentation. My question is regarding particle milling process and size monitoring during the procedure. So if starting, for instance, at 20 micrometers and you need to reach 500 nanometers, what would be an adequate technique to follow the size from 20 micro to 500 nano? Do you have any answer?
So my answer is a little bit of a disappointing because most techniques that we've worked with are in the nano range. The nano range officially starts from 100 nanometers below, and some techniques can also measure up to like 500, but above 500, I do not have experience. I mean, for the biggest one, you would use optical microscopy, but there is this in-between size where I don't know. Maybe Yuri has a better idea. There is this hyper-resolution optical microscopy. If this can work, maybe.
No, I do agree with you, Christian. So that it's very challenging, this middle earth region, no, to characterize, no. So we'll add to the pool maybe a laser interferometry that sometimes is used also to assess in this range, but it's quite challenging, no. It's quite challenging. So it's a very good scientific question.
Okay, the next one. The next one comes from Valentin from LNE. Thank you. By the way, hello, Valentin. Thank you for the presentation. Do you know if there are ways to convert one equivalent diameter to another, or at least quantify their differences?
This is probably a question for me again. So if you have a mean diameter in volume, number, and intensity base, then you can convert them if you have the full size histogram. So if you have the number-based histogram, you multiply by x to the third power, radius to the third power, you get the volume-based histogram, and from that you can decide it. And if you assume something like a log normal distribution, even on Wikipedia, you can find the formula to convert it. But it's impossible to convert hydrodynamic to core diameter. You need to know the sample.
Because of the shape?
Because yes, it's if you have only the core and there is some arbitrary shell, it can be small, it can be large. This one technique doesn't see it, so yeah.
Crystal clear. Let's go to the next one, which is linked somehow with my comment. Brenduza asked a good, nice question, as always. Thank you for this session. With the spherical particles, DLS is very good. What about the particles with different shapes? Is DLS reliable for them?
That's a very good question, and the answer is no. So it's not reliable. It's very, very hard because what you measure is the effective hydrodynamic radius, and then you got a size value, but that does not necessarily correspond to any of the geometrical features that you will see in microscopy.
Okay, maybe Clémence, you have a question also. I do have one or two more, and then we'll shut down the session. But maybe you have one, Clémence, because we all struggle in the lab with Carac.
Yeah, actually, I had one. So this time I was more about particle concentration because from the emoji map, which I loved, I saw that it doesn't seem to be like a perfect technique. So maybe could you give example of what would be your go-to technique to assess the nanoparticles concentration?
So I think that if you have nanoparticles and they are large enough, you could go with NTA. It's relatively inexpensive, and it in previous comparisons it has shown that it gives reasonable results. But the problem is it depends on the material, the result, and it's not traceable. So you do not get uncertainty validated result. It's for a quick shot, it's good.
Okay.
Otherwise, if this electron microscopy thing is going to work, then this will be a breakthrough because electron microscopy can work with all sorts of particles. They can have any arbitrary shape. They can have great polydispersity, no problem, because you see the individual particles. And there is also another one, if the particles can be seen, this kind of technique, flow cytometry that's used in the hospital. It's also a great technique if you don't hit the limit of detection.
Okay, thanks.
Fantastic. I have a last question, which is more of a troubleshooting, and then some information for you, and a really last poll that lasts 10 seconds. So if you can stay until the end, 5 minutes, and we're all done. Guys, okay, this is perfect. You are experts. I mean, you know the deal, but sometimes in the lab, you just have two methods that disagree and you don't know what to do with this. So what would be your best advice? What to look first to decide if it's a real difference or if it's just a measurement artifact? What is a good practice? Not to choose one among the others, but at least to understand what's happening when two methods gives different measurements.
Send the sample to a different lab.
Okay, thank you for the transition, Christian, because next time we'll talk about interlab comparison together with Enrica and Jeremy. So first of all, thank you so much. I would like to take 15 seconds for a last poll. It's more for us, in fact. We would like to see if you're interested in more decision-making tools inspired from the great, very simple heat maps that you've seen today. So if you can just answer that in 10 seconds, that will help me a lot. So if Metrino developed the following tool this year before June, how valuable would it be for you? A heat map, no guidance. The emoji were great. I mean, we don't need more than that. Do you want more like a printable lab poster that you can put in your lab to explain more today what is a good or bad measurement methods to use for each thing? A decision tool for sample prep, a calculator of uncertainty online, or a decision chatbot. You need to decide between it's a game changer or it's totally irrelevant for me. So please use this tool for 15 seconds. You would not believe how useful it will be for us if you take the time to do that, because we don't want to reinvent the wheel or to spend 1 month with Clémence to transform something in more fancy that you will never use. While you answer that, I want to share some 3 final slides. Okay. Clémence, can you see the right slide?
Yes, we can see.
Okay, so just to let you know while you still answer our last questionnaire is that you can save the date of the next session. The third session of the Metrino Academy will be also a great one, dedicated to RNA LNP measurement across laboratories. So it's called Tiny Particles, Big Challenge. And it will be a mix of how to nicely measure what is inside and outside your LNP, if I may, with Jeremy Parot from Sintef and Enrica, indeed our package leader from LNE. Enrica, you're here, by the way. I saw you. So yeah, it will be in exactly 1 month on Thursday, March the 5th, exactly at 3 p.m. Also,
can you just click on continuer de partager?
Yeah, I'm sorry. I want to continue to share with you guys. This is the mood. Yeah, so please enter our satisfaction survey. You will receive a quick email after that by Zoom. Nobody opened Zoom emails. Please do it and click on the right satisfaction survey. To us, it means a lot because we shape the next one also according to your feedback today. I guess that also Clémence will give you just the link, the direct link in the chat. It takes 30 seconds, but it's important to us. And last but not least, if you're interested in Metrino and you want to get in touch with us, you have a simple contact email address. But also by just checking this QR code, you have access to all the LinkedIn page, website, etc. It's very practical. And yeah, we are joining the last phase of Metrino. We will stop in June, and we have a lot to share for you guys. So please use us as much as possible and stay in charge and stay in contact. Sorry. Okay, I will now close the poll and show you the results. I guess that you're all quite interested in all of that, right? Because I see a lot of interest. Would it be very useful or a game changer? Would it be the lab poster, the heat map, sample prep, decision or uncertainty calculator? A bit less for the decision chatbot, and I thank you for that because it would have been horrible effort on our sides. But I mean, we will do our best to produce that content together with Yuri, with Metrino work package leaders, and together with Clémence, because I see possible great value output of Metrino project for you guys. With this, I would like to close the event by leaving the floor to Christian and Yuri for a last comment. Did we forget to say anything, guys?
I want to just thank you everyone for attending this and to give me the opportunity to present metrology to non-metrologists.
Thank you. Thank you for everyone for the patience. Yeah.
Yeah, I mean, that was super useful. I hope so. Please answer our satisfaction survey. A big thanks also to Clémence Nadal for the preparation of this great webinar. And I wish you a fantastic rest of the day, and we'll talk to each other in 1 month from now. Bye-bye.